So today we're going to talk about one of the most powerful tools out there, thinking like a scientist. And I know what you might be thinking, lab coats, beakers, but it's not just for them. It's really a way of looking at the world that connects something as simple as your morning routine to, these huge world-changing discoveries. Let's get into it.
All right, let's just start with a kind of weird question. What on earth could oversleeping possibly have in common with figuring out what causes a disease? I know, it sounds totally random, right? But the answer is that they're both powered by the exact same way of thinking, of questioning, and of finding proof. Because here's the thing, the real magic of science isn't a bunch of facts you memorize. It's a mindset. It's a way of approaching the world with this really powerful combination of curiosity and, well, a healthy dose of skepticism.
And it all really boils down to three key ideas, three pillars. First, you've got curiosity. That's the engine, right? The little voice that's always asking why or what if. Then you have skepticism, which isn't about being negative. It's about critically looking at things and asking, are we sure about that? And finally, logic ties it all together, letting us build conclusions that are actually based on evidence. And that word, evidence, is absolutely crucial. The whole process is built on something called empirical evidence. We're not talking about feelings or guesses here. We're talking about cold, hard, observable facts. Things you can actually see, measure, and double-check. That's really the foundation for everything in science.
Okay, so to see how this all works in the real world, let's go back to that oversleeping problem. We're going to solve this little mystery like a scientist would. And honestly, you'll probably realize you already do this every single day without even thinking twice about it.
First things first, we need a hypothesis. Now, in science, a hypothesis isn't just any old guess. It's a proposed answer to a question, and this is the most important part, it has to be testable. It's got to be something you can actually go out and check.
So you wake up late. That's your observation. Your brain just immediately starts firing off possible explanations, right? These are your hypotheses. Maybe the alarm just didn't go off. Or, classic mistake, maybe you set it for 7 p.m. instead of 7 a.m. Or, hey, maybe it worked perfectly and you just slept right through it. Boom, you've just come up with 3 clear, testable hypotheses. And now for the most critical step, you have to test it. The ideas are great, but they're not enough. So you pick one. Let's say the alarm was set for the wrong time. You grab your phone, you check the alarm settings, and there it is, the evidence. It was set for 7 p.m. Your observation supports that hypothesis. Mystery solved, all thanks to some good old scientific thinking.
So that's the basic loop, right? Observe, hypothesize, test. Now let's see what happens when we scale that up from our everyday problem to a formal, rigorous scientific experiment. The core ideas, they're exactly the same, but everything just gets a lot more buttoned up. In a formal experiment, we talk about variables. The independent variable is the one thing, and only one thing, that the scientist is intentionally changing. So, for example, if you're testing a new medication for blood pressure, the independent variable would be the dose of that medicine. And of course, if you change something, you've got to measure what happens next. That's where the dependent variable comes in. It's what you observe and measure. It's your data. So in that medication trial, the dependent variable would be the patient's blood pressure. Its value, you see, depends on the change you made. And really, this relationship is the whole ballgame. This is how you establish cause and effect. Does changing this one thing, the independent variable, cause a predictable change in that other thing, the dependent variable? You're literally changing the cause to measure the effect. But, and this is a big but, to make sure you can trust your results, you gotta run a fair test. That means keeping everything else the same for all groups. We call those constants. It also means you need a control group. That's a group that doesn't get the new medicine, so you have a baseline to compare your results against. Okay, now we need to talk about something really important, because it's probably one of the biggest mix-ups when people talk about science. It all comes down to one little word: theory. I mean, we've all heard someone say this, right? Oh, that's just a theory. It's almost always used to mean it's just a guess or a hunch, something that's not proven. But in the world of science, that could not be more wrong. So let's just break this down. What most of us call a theory in casual conversation is actually much closer to what a scientist would call a hypothesis. A real scientific theory, that's the big one. That is a massive, powerful explanation that covers a huge range of observations and is supported by an absolute mountain of evidence. A scientific law describes what happens, like gravity pulls things down. A theory is our best explanation for why it happens.
So you see, a scientific theory isn't the starting point for an idea. It's kind of like the finish line. It represents the absolute pinnacle of our understanding, built from countless hypotheses that have been tested and tested and tested again. That's why things like germ theory or the theory of natural selection are so foundational. They're the most powerful, evidence-backed explanations we've got.
But, and this is probably the coolest part about science, nothing is ever set in stone forever. Take stomach ulcers. For decades, the accepted wisdom backed by evidence was that they were caused by stress. Made sense, right? But then new evidence came along from two scientists showing that actually a specific type of bacteria was the real culprit in most cases. And so the science changed. Because that's what science does when faced with better evidence. And that story perfectly illustrates this idea. Science isn't some straight road to a final, perfect answer. It's much more like a living, breathing cycle of discovery that's always refining and improving what we know about the universe.
You see, it's not a list of steps you do once and then you're done. It's a loop. You observe something, you form a hypothesis, you test it, you analyze the data, but that last step, evaluating the results, that almost always sparks new observations and new questions, which sends you right back to the beginning of a loop. It just keeps going.
And a really important part of keeping this whole cycle honest is something called peer review. Before a new study gets published and accepted, other experts in that same field, total strangers, go over it with a fine-tooth comb. They check the methods, they check the data, they check the conclusions. It's like a built-in quality control system to make the science as strong as it can possibly be.
Which brings us right back around to where we started. We've seen that thinking like a scientist is all about being curious but skeptical and building your ideas on hard evidence. And that process leads to theories, our most powerful explanations for how the world works. So, I'll leave you with this to chew on. If a scientific theory is the best, most evidence-backed explanation we have, what would it actually take to change it?